Welcome to this year's Nobel Lectures in Chemistry. In fiction and popular culture, a catalyst is an inciting incident which initiates the subsequent story. For the present story, the catalyst might then be defined as the Swedish chemist Jöns Jacob Berzelius, who in 1835 formulated a concept about a catalytic force and catalysts. Some years later, this concept was refined by the Latvian chemist Wilhelm Ostwald. He articulated the idea that a catalyst is a substance that accelerates the rate of a chemical reaction without being part of either the reactants or the products. It is a beautiful idea. The catalyst participates in an event, but is not consumed by it and remains unaffected. In 1909, Ostwald was awarded the Nobel Prize in Chemistry for his work on catalysis. So where is this story heading, you might ask? We all have an intimate relationship with molecules, but most of the time we are just not aware of it. It might be drugs, agrochemicals, molecules that can store and relay information, or that can harvest sunlight and convert it into electricity. Our knowledge of how to design and make such molecules in an efficient and sustainable manner is closely linked to the progress of our society, and it often involves catalysis. As a matter of fact, the formation of almost all molecules that we are made of and use in everyday life involve catalysis. Many organic molecules can exist as non-identical mirror images of each other. It is just like with our hands. Same, but mirror images. Such molecular mirror images can have different properties. For example, one mirror image of a medicine can have the desired effect, while the other has an underside or no effect at all. There is thus a need to be able to selectively produce only the mirror image of a molecule that has the desired property. Today this can, for example, be achieved by using enzymes or asymmetric metal catalysis. The use of low molecular weight organic molecules as catalysts for chemical transformation is not a new phenomenon. Indeed, it can be traced back to the year 1860, when the German chemist Liebig reported that acetaldehyde catalyzes the hydrolysis of cyanogen into oxamide. The work by Benjamin List and David MacMillan in the year 2000 resulted in a turning point. There is a very clear before and after. They conceptualized the area of asymmetric organocatalysis and have provided organic chemistry with a powerful tool for selectively making only one of the two possible mirror images of organic molecules. Since then, the research area has exploded, and as a result, we today have a number of small organic molecules that catalyze many different reactions. These catalysts can be used to manufacture molecules for our society. Organocatalysis also holds great promises as a sustainable technology. We are now looking forward to the lectures by this year's Nobel laureates in chemistry. Benjamin List was born in 1968 in Frankfurt am Main in Germany. He obtained his PhD in 1997 from the Goethe University in Frankfurt. He is currently director at the Max-Planck-Institut for Kohlenforschung in Mülheim an der Ruhr. Benjamin List, I now welcome you onto the stage. We are very much looking forward to your lecture.
Ladies and gentlemen, I'm deeply honored with this great recognition, and I would like to thank the Royal Swedish Academy of Sciences, as well as the Nobel Committee and everybody else who was involved in making this amazing prize a possibility. I would also like to use this opportunity to thank my brilliant and really truly awesome co-workers that I had the pleasure to working with during the last 22 years for their hard work, dedication, and their brilliant ideas that they brought into this fantastic adventure. And last but not least, I would also like to thank all the other scientists that during the last 2 decades or so have made organocatalysis what it is right now, a vibrant, very dynamic, very productive field that has really made a change to chemical synthesis. Thank you all so very much. I am deeply fascinated with the science of catalysis because if you think about it, a catalyst, by providing a lower energy pathway to convert substrates into the desired product, is as close as chemists can ever come to magic. Because if you think about it, this providing a lower energy pathway enables us to use a tiny little amount of a catalyst to convert large amount of starting materials into a useful product or material. And this is something I find incredible. But the beauty of catalysis is that it is also a very important technology. Some would even say perhaps the most important technology that we have on the planet for humanity. And in fact, people have estimated that catalysis contributes to roughly 1/3 of the GDP. These are figures in the trillions. And I would also say that probably there is no other technology who could claim to feed, to heal, to warm, and to transport us and our goods. The last point I'd like to make for catalysis is that the challenges humanity faces right now, global warming, energy conversion, all these issues will have to be addressed with the help of catalysis. And I have no doubt that catalysis will continue to deliver like it did in the past. Now, by no means am I the only one interested in catalysis. In the history of chemistry, this has always been a very, very appealing concept to chemists. And this is also reflected in the history of Nobel Prizes that were given to catalysis researchers. The very first catalysis Nobel Prize was given in 1909 to Wilhelm Ostwald. And Ostwald actually was recognized for his pioneering studies on the general physical-chemical aspects of catalysis. But Ostwald also was very much aware of the fact that enzymes, which were known to be efficient asymmetric catalysts, are by no means different to the chemical catalysts that chemists have made. And there's one interesting vision that Ostwald proposed in 1905 in a book review actually, in which he suggested that one day chemists will be able to create organic catalysts, as he called them, organische Katalysatoren, that rival the selectivity and efficiency of enzymes but are thermally more stable. And this was expressed in 1905. So quite remarkably actually, his graduate student, Georg Bredig, in 1910 realized this vision already by describing a cinchona alkaloid catalyzed HCN addition to benzaldehyde, and this is actually a reaction that is also catalyzed by enzymes, and Bredig found in a reproducible way that enantioselectivity was actually obtained in this process. Remarkably though, chemists have at that point chosen to almost completely devote their attention to transition metal-based catalysts. And this is reflected again in a history of amazing Nobel Prize winners. For example, Sabatier in 1912 discovered that finely dispersed transition metal powders can actually catalyze hydrogenation reaction of organic compounds. And along those lines, Haber and Bosch, of course, discovered what is probably one of the most important chemical reactions for our life on this planet, the Haber-Bosch synthesis of ammonia, which is a heterogeneously catalyzed hydrogenation of nitrogen to give ammonia. Bergius developed coal hydrogenation processes, again with the help of heterogeneous catalysts that delivered fuels, and those were at the time, of course, very useful and important. A big change then occurred actually in 1963 when the first Nobel Prize was awarded to work on homogeneous transition metal catalyzed reactions, and that the starting point happens to had occurred in Mülheim actually, in my institute, the Max-Planck-Institut for Kohlenforschung, when Carl Ziegler discovered homogeneous transition metal complexes that would catalyze polymerization reactions of ethylene and propylene that he and Nutter studied and won the Nobel Prize for in 1963. And that marked the beginning of homogeneous transition metal catalysis. The next 3 Nobel Prizes in this series also went to that area. The one that is probably the most relevant for my presentation today and for this Nobel Prize is the Nobel Prize to Knowles, Sharpless, and Noyori, given in 2001 for their pioneering contributions to asymmetric catalysis of redox reactions, hydrogenations, and oxidation reactions. And only 4 years later, another Nobel Prize was given to a homogeneous transition metal catalyzed reaction, the olefin metathesis, to Schrock-Grubbs and Chauvin. And only again 5 years later, another Nobel Prize for the same general area was given to Heck, Negishi, and Suzuki for their pioneering studies on cross-coupling methodologies using transition metal catalysts. So you can say basically the last century was the century of transition metal catalysis. The only exception was actually the recent Nobel Prize to Frances Arnold for her pioneering contributions to the directed evolution of enzymes, biological catalysts that then can be more efficient or catalyze reactions that are unknown in nature. And so with this background, you probably understand the situation that I found when I was a graduate student in the mid-90s, and that was chemists were essentially convinced that when it comes to asymmetric catalysis, the selective production of mirror image molecules, there are only 2 options available. You can either use enzymes, and as I said, this was already known to Ostwald at the time in 1905 or even before that, or you can use synthetic soluble transition metals as reflected with a Nobel Prize in 2001 to Sharpless, Noyori, and Knowles. And so this was the mindset, and that was the time when I was considering what to do during my postdoc, and I became fascinated with this idea of creating artificial biocatalysts that would engage in the catalysis of non-natural reactions. And at that time, in the mid to late 90s, one approach appeared to be particularly attractive to me, and that was catalytic antibodies. And I was very fortunate to be able to move to the Scripps Research Institute and to work with Professor Lerner and Barbas on the utilization of aldolase catalytic antibodies. They had just discovered an aldolase catalytic antibody that would catalyze with high efficiency and also very high selectivity aldol reactions. And I was excited to work in this field all of a sudden, and I used this antibody to do large-scale experiments, gram-scale experiments. I also used this antibody in the synthesis of natural products, actually. But the main thing I was interested in was to understand how this antibody actually does its catalysis. And fortunately, at the time, a crystal structure of this antibody was available, and what that revealed was that in the active site of the antibody, you have on the one hand an amino group derived of a lysine residue, and then a water molecule that bridges this amino group to a tyrosine hydroxy group. And for me, this immediately suggested that perhaps the mechanism is in fact a bifunctional mechanism where you have an amino group that, assisted by the acid group, engages in the formation of an iminium ion from a ketone precursor. And this iminium ion formation is actually quite important. It not only lowers the LUMO energy of this system, but it also drastically increases the alpha CH bond acidity. This has been estimated by Bill Jenks already in the 60s, I think. This was done in the context of work on the mechanism of class 1 aldolases. And so now the conjugate base of this acid co-catalyst can now abstract a proton to generate an enamine intermediate. So as you can see, this is basically a strategy that biology has developed or evolved, one should say, to enable carbanion equivalent formation under physiological conditions in water without the availability, of course, of stoichiometric organometallic bases. So this enamine then can engage in a direct CC bond formation with an aldehyde, for example, again assisted by the Brunstad acid co-catalyst, which protonates the nascent oxyanion in the transition state to generate the iminium ion of the aldol product, and then hydrolysis occurs once again assisted by the conjugate base of this acid co-catalyst to generate the aldol product and to regenerate this bifunctional enzyme, as I like to call this. So that was the thinking that I developed, and this, in fact, encouraged me much later in January of 1999 when I became an assistant professor and when I was thinking about my independent work to think again along the lines of Oswald. Why is it not possible to design organic, simple molecules that have all the machinery that is needed to catalyze such an aldol reaction? And I realized all that is needed is an amino group and an acid group, right? And so with that, I started to designing potential small molecule catalysts when I remembered, of course, there already is a catalyst like this. There is an amino acid, in fact, that catalyzes aldol reactions, and that is, of course, proline in the famous Hayos-Parrish Eder-Sauer-Wiechert reaction that was very well known to me, of course, since my undergraduate studies in Berlin. And in this process, proline catalyzes an intramolecular aldol reaction to give these bicyclic ketones, which the idea had been could be useful intermediates in developing industrial routes to steroids. This never became a reality, in fact, because steroids are made from natural products and the supply of these natural products was sufficient. However, it was still an important discovery, somewhat an underappreciated discovery. People were slightly confused, I think, about the mechanism. But in that moment, I realized actually what is probably happening is that proline is just the essence of an aldolase enzyme. It has all that is needed. It has an amino group, actually a privileged amino group for iminium ion and enamine formation, and it has a carboxylic acid that can act as the co-catalyst, the Brunstad acid-base co-catalyst. And so this is the hypothesis I developed as a fresh assistant professor at Scripps. I hoped that proline would function like a microaldolase, as I called it, by converting first the ketone assisted by the Brunstad acid into the corresponding iminium ion, and then the carboxylate would deprotonate this iminium ion to form the corresponding enamine, and the enamine in turn would then be able to react with an aldehyde to form the carbon-carbon bond, where the proton is transferred in the transition state onto the oxygen, the oxyanion of the aldehyde that is being formed. And then the iminium ion in the last step would be hydrolyzed with water to form the aldol product and regenerate the proline catalyst. This was the hypothesis I developed. It's kind of actually one of the few catalytic cycles that I designed and that then, when I did the experiment, actually worked. And this is also what happened in this case. I was very excited when I discovered that indeed proline also catalyzes intermolecular aldol reactions of ketones with aldehydes to give very valuable aldol products in really excellent yields and state-of-the-art enantioselectivity also. And I think it is important to mention in this context that the so-called direct asymmetric aldol reaction at the time was considered one of the biggest challenge of asymmetric catalysis, and there had been only one solution to this problem, and that was a sophisticated lanthanum-based, fancy transition metal-based catalyst that was developed in the group of Shibazaki in Japan. And all of a sudden, it turns out there is now an edible, non-toxic, readily available catalyst that gives the same kind of reactivity with state-of-the-art selectivity. For me, this was a big breakthrough. I was very excited at the time, and we were really happy to see that the reaction was also not limited to one aldehyde, but in fact, we could convert several other aldehydes as well to give the desired aldol products, in some cases really with enormous enantioselectivity. In fact, we have just submitted a manuscript to Organic Synthesis, which allows in a reproducible fashion for hopefully all undergraduate students in the world to do these experiments on a gram scale. So that was quite exciting. But already during those studies, I realized there is probably more in this kind of chemistry. Proline is not just a microaldolase. Proline is a catalyst that can convert carbonyl compounds catalytically without requiring a stoichiometric reagent or an auxiliary into the corresponding enolate equivalents, right? And so this then led to what we have called, and MacMillan also, my co-laureate, a wonderful colleague by the way, what we have called a generic activation mode for organocatalysis. So proline actually has this generic activation mode that we have called enamine catalysis. It converts carbonyl compounds into the corresponding enamine. And now this enamine, of course, should not only be able to react with aldehydes in aldol reactions, but it should in principle be capable of reacting with any type of electrophile. So in principle, it should be able to react with an imine, it should be able to react with a Michael acceptor, even alkyl halides, how about oxygen, nitrosobenzene, dialkyl azodeicarboxylates, and all of these wonderful electrophiles in principle should, according to this catalytic cycle design, engage in such transformations, CX bond formations. And so this was then the program of the following years. And indeed, I could show with my slowly growing group that enamine catalysis is actually a solid concept, and we discovered a number of different reactions. I should also emphasize that in these early days, we initiated a collaboration with Professor Ken Haug at UCLA, and that was a very fruitful collaboration in which he provided theoretical computations on the mechanism of our reaction, while we in the meantime did kinetic studies and other mechanistic work, and all of that boiled down to what is now called the Haug-List transition state of the aldol reaction. And I said this before, who knows the final truth of this mechanism? In any case, this model has a very powerful predictive character, and all of the reaction I will be discussing with you today could have, or indeed had been predicted on the basis of this transition state. For example, our proline-catalyzed aldol reaction, the stereochemistry of this is well explained with the Haug-List transition state, and so is the stereochemistry of these other two intramolecular aldol reactions we discovered, the enol exoaldolization of dialdehydes to give cyclic aldols, and also the first catalytic asymmetric transannular aldolization to give these natural product precursors that we indeed have used in very efficient natural product syntheses. But in addition to carbonyl compounds, as I said before, you can also use other electrophiles. For example, we were excited to find the very first example of a catalytic asymmetric alpha alkylation of an aldehyde. And that is a novel type of reaction because it's not an addition reaction, but it's a nucleophilic substitution reaction. And it also gave cyclic products in excellent enantioselectivities. And already back in 2000, we had shown that Mannich reactions, actually the first catalytic asymmetric three-component Mannich reaction of a ketone, an aldehyde, and an amine can be catalyzed with proline once again. And we made these ketones here, but also a number of other products based on this very general and very powerful and highly useful Mannich reaction. For example, acetaldehyde-derived Mannich products in really excellent enantioselectivity. And last but not least, I would also like to emphasize one example where not a CC bond is generated, but in fact a CN bond in the formation of these alpha hydrazidoaldehydes, which are great precursors to making alpha amino acids actually. And we found that this reaction can once again be catalyzed by proline with very good selectivities and also very good yields. I should at this point again emphasize that this became more and more a field, and many different groups have started to engage in studying enamine catalysis and developing novel reactivity and novel reactions. And this is just a small fraction of all the beautiful transformations that were discovered during those days. Some people called them the gold rush in organocatalysis. But I would like to still highlight one additional reaction that I think is kind of timely, and that was a proline-catalyzed intermolecular aldol reaction of two different aldehydes. This is actually a development that goes back to work done in my laboratory, that was later then advanced by my co-laureate, Professor David MacMillan. And the group at DSM, actually in the Netherlands, found that this cross-aldolization of two different aldehydes gives an aldol product that can be readily converted into darunavir. And darunavir, as the name suggests, is an antiviral agent, and it is used for the treatment of HIV infections. And this probably has been one of the worst pandemics of all time. And it's really rewarding to see that organocatalysis has really contributed in making this more like a treatable disease, and you don't hear so much anymore about this pandemic. However, enamine catalysis, of course, is not just the whole story. In fact, this is just one example of a generic activation mode that was developed in the context of organocatalysis. Many other generic activation modes have been developed in the meantime. For example, of course, iminium ion catalysis. This is Professor MacMillan's main area of research in the early days of organocatalysis, and he has used this very elegantly in cycloadditions and in conjugate additions. But as I said, it also forms the basis of enamine catalysis by this acidification of the alpha CH bonds. But there are other also very powerful generic activation modes. Consider, for example, anion binding catalysis, where hydrogen bonding catalysts bind to anions to generate supramolecular chiral anions that then can engage in nucleophilic addition reactions, for example, with very high enantioselectivity. Very fruitful concept that has led to numerous very important publications in the field of organocatalysis. Acyl ammonium ion catalysis is yet another generic activation mode of organocatalysis, where acyl groups are transferred from one substrate to another substrate, and it's also a very powerful organocatalysis strategy widely used all over the world. Carbene catalysis, a very unusual mode of reactivity that is actually quite old, but that also has been massively advanced during the last 20 years, where aldehydes are so-called umpoled, so the aldehyde, which is normally is an electrophile, is converted into a nucleophile. And this unusual reactivity can be utilized in many different, very elegant and important transformations. And last but not least, the only additional generic activation mode I would like to show here today is, of course, Brunstad acid catalysis, because of its very high importance that it has gained in recent years, and I will say more to that in just a minute. Suffice to say that this is again just a small collection of generic activation modes that came out of organocatalysis. There are many, many more, and all of these generic activation modes have led to numerous different transformations, some of which are even applied on a technical scale in the synthesis of pharmaceuticals and scent molecules, for example. Now, at this point, it's also helpful, to organize organocatalysis. And I have found a very useful way in doing so, and this goes along the definition that I prefer, and that is organocatalysis is the catalysis with small organic molecules, where a metal, of course, is not part of the activation principle, and that function by donating or removing electrons or protons. And that automatically creates 4 sub-areas of organocatalysis: Brunstad acid catalysis, Brunstad base catalysis, Lewis base catalysis, and Lewis acid catalysis, and these are the catalysts that either donate or remove protons or donate or remove electrons. And this actually brings some nice organization into the field of organocatalysis, and it also brings to the surface gaps where actually nobody works on, I found. And in my lab, we became particularly interested in the utilization of Lewis acid catalysts. And this is what we are doing actually right now. We are really fascinated with the power and potential of acid catalysis because of its universality. Because after all that acids need for catalysis is electron density, and this is pretty much what chemistry is all about, electron density, right? And so we realized that actually possibly the vast majority of all catalyzable reactions can be catalyzed with acids. And so over the years then, we have advanced our little proline molecule, which is a Brunstad acid, don't forget that it has a pKa of around 20, to much more acidic and also more complicated acids that in the meantime have reached acidities in the pKa scale in acetonitrile of below 2 units. So that means these rival the acidity of superacids and trifluimide, for example. But in addition to this, they have a unique feature, and we call this confinement. So around this acid functionality, a confined pocket evolves with this catalyst design, simulating somewhat how enzymes catalyze their reactions. And with this special combination of high acidity and confinement, a number of unique transformations have been realized in recent years, and I would like to highlight 6 of them to you. Number 1 is a cross-aldol reaction, or a Mukayama-aldol reaction of the acetaldehyde-derived enolsilane with yet another aldehyde to give the corresponding aldol product in excellent enantioselectivity. Looks kind of simple, but in fact it's an amazing transformation, because previously this combination of an enolsilane of acetaldehyde with yet another aldehyde would just lead to polymerization, because as surely you have noticed, both the starting material and the product have an identical functional group, an alpha unbranched aliphatic aldehyde. And yet, with the magic of these confined acids, the product is simply not a substrate anymore for the catalyst, and it ends after a single aldolization to make these very important aldol products. We can also catalyze other Mukayama aldol reactions. For example, Mukayama-Aldo reactions of ketene acetals with ketones. And that was a challenging reaction at the time. And not only can we do this, but we can do this with parts per million catalyst loading. In fact, in this paper, we describe one example where we use below 1 part per million as the catalyst, which I think is the lowest catalyst loading that has ever been used in any catalytic asymmetric carbon-carbon bond forming reaction. There might be enzymes that are as good as this, but I'm at least not aware of them. We can catalyze Diels-Alder reactions, but not just the usual ones, but very challenging ones where we combine unreactive dienes with unreactive dienophiles and make these cyclohexene products for the first time catalytically and with high enantioselectivity. We can also catalyze hetero-Diels-Alder reactions of now all types of dienes with all types of aldehydes to give these useful products here, and it's kind of remarkable to realize that such a transformation was unprecedented even with achiral catalysts. So it's actually even unusual reactivity that is enabled by these confined strong acids. We can also now, with this high reactivity, finally activate olefins for asymmetric catalysis. This has been the domain of transition metal catalysis, but now actually organocatalysis for the first time can also enable the activation of simple olefins, in this case to form the corresponding carbocations, which then engage in a nucleophilic addition to form tetrahydrofurans. And very last but not least, I would like to share one recent discovery in my group. We have found that ID-pi catalysts can actually mediate the addition of TMS cyanide to 2-butanone. Looks simple, but it turns out this product of this silyl cyanation reaction is a valuable intermediate in the synthesis of 2 pharmaceuticals. And it also turns out that all previously developed chiral catalysts for silyl cyanations and hydrocyanation reactions, and these include very sophisticated transition metal complexes, even more sophisticated organocatalysts, and also very advanced enzymes and even engineered enzymes, and none of these catalysts was able to deliver this product with greater than 95 to 5 ER. So this is actually a milestone, I would argue, in the history of organocatalysis. We're very excited about this because finally this idea of Oswald that chemists are now able to design organic molecules that enable enzyme-like selectivity and reactivity seems to become true. And I think we're just opening a door here, and I expect still an exciting and a great future for asymmetric organocatalysis, and I'm very, very happy to be part of this. So with this, I would like to finally thank my wonderful co-workers who have supported this adventure during the last 20 years. I had the privilege to work with amazing, brilliant, hardworking, and very creative people during those years, and I would like to thank all of them wholeheartedly. I would also like to thank the funding agencies that have supported us. Most importantly, though, the Max-Planck Society, which has given me the freedom and the privilege to really pursue an idea to the depth that I wanted it to pursue. And this was really a great honor, and I feel very happy to have been part of this awesome club. And last but not least, I would also like to show you a picture of October 6th when we celebrated at our institute, and it was really a delight to see the joy of all the co-workers of our Max-Planck-Institut for Kohlenforschung in Mülheim, the woodworker, the steelworker, the glass blowers, the cleaning personnel, the administration, my colleagues, all the graduate students and postdocs, the technicians. It was just an institute in an excited state, full of joy, and that made me even more happy, and I feel really, really honored and rewarded with this. If you're interested in the names of all the co-workers that have worked in my group, they're listed on this PowerPoint here. And last but not least, I would like to acknowledge the most important people in my life. Meine geliebte Familie, vielen Dank, ihr Lieben, meine süßen Jungs und meine Frau, dass ihr in all den Jahren so an meiner Seite gestanden habt und Katalyse-Fans geworden seid. 1000 Dank.